All right, so we're going to put our calculators away. We're actually not using our calculators for the rest of this unit, including the test. Okay. And last class, we introduced a very important calculus concept of an infinitesimal. You know, a limit meaning we're getting close to a specific location, very, very close to a specific location, but not exactly at that location. And we're seeing our function values approaching or getting closer and closer to a specific number. Okay? And it might not ever equal that number, but it's getting closer and closer and closer. It's approaching that number. We got to keep that concept in our brains. That's a very important calculus concept. However, for the next two lessons, we will find like that key concept of calculus is not used much. Okay? We instead use limits to help us review some algebra. Okay? And we will use algebraic means to find limits. And really the next two lessons are just lessons where it's like, hey, you remember how to factor? Hey, do you remember how to simplify this? So remember that concept of approaching and getting very, very close to, but we don't have to worry about it so much. We're going to focus on, you know, algebraic simplifications and reviewing algebra. So we're going to try to find limits like the limit as x approaches 1 to this function by hand. Okay? Now it's important to know that, you know, with most functions, limits equal our function values. You know, if something connects smoothly, is continuous, doesn't have any holes or jumps or asymptotes, to find a limit, it's easy. Just find the function value. Plug in 5. And you get 13. That's the function value. Guess what? That's also the limit. We don't have to know that the graph of 3x minus 2 looks like this. We don't have to know that at 4.9999 we're at 12.999. We have the function value and we are approaching that function value. Okay? So don't need that. Same with the graph of sine. Sine of x exists for any value. And to find its limit, we just need to plug in pi or whatever value we want to into sine. And boom. So most functions we work with are continuous. They have limits everywhere. And the limits equal the function values. Fantastic. So let's go back up to this guy and let's see if we can do the same thing. Let's plug in 1. And I get 1 squared minus 1 over 1 minus 1. Ugh. I got a problem. We have 0 over 0, which is undefined. Well, if I had a calculator, my next thing would be to plug in values very, very close to 1. So I would try to find f of 0.9999 or f of 1.001 and see if we're approaching a specific value. But without a calculator, this is not reasonable. Okay? Well, most of us, if we encounter something like this, right now we're thinking, let me just answer that this limit does not exist. Okay? Usually students, if they feel like they're stuck, they just say the limit doesn't exist, and they circle E. Usually E on one of your multiple choice questions will be does not exist. But I've graphed this already, and I can show you that the graph of x squared minus 1 over x minus 1 it's a very loud bell. So loud. You can see that around 1, we're definitely approaching some y location to the left and to the right. Okay? So even though I can press trace, I try to find the value 1, and the y is blank. That shows you that it's undefined. What we have in this situation is the location of a hole. Okay, but we know that as long as we're approaching the hole from the left and from the right, and it's the same location, that the limit exists. So this limit exists. Does not exist is wrong. But what am I to do? Well, I can kind of inspect this function a little bit more. And I notice I got x squared minus 1. And I know from my days in Algebra 1 and Algebra 2, and all of my math classes, that I could factor that. That's a difference of squares. I could turn this into x plus 1 times x minus 1. Okay, well, let's just kind of rewrite it. And then, whenever we see something over its same thing, we just want to cancel. And yeah, let's go ahead and do that. Only, when we do that, we have changed the original f of x. When we eliminate something, we have created a new function. I'm going to call this new function g of x. It doesn't have to be g. It can be anything, as long as we know that it's different from f. And what's great about g, unlike f, I couldn't plug in 1 into f. I got 0 over 0. Don't know what that is. But I can plug in 1 into g. And I get 2. Okay, great. 2, is that my answer? I don't know. Well, let's kind of inspect how similar is g to f. You know, like g came from f, but it's not the same thing. What's different about it? Well, let's go ahead and graph g, graph the x plus 1. I love how this is in red. So we have the blue line already down, and we can see that happened very quickly. The red line goes right on top of the blue line. So it turns out they're practically the exact same function, except for one point. For f at x equals 1, we see this error. That's the whole undefined value, that's the whole. But for g at 1, we see 2. Well, g tells us the location of that hole, and g helps us discover the value of this limit. So g is the exact same thing as f, except it has the point at the location of the hole, and it tells us what the limit is. Tells us the y location of the hole. So turns out g of 1 is 2, and that is the limit as x approaches 1 of that original function. Okay, so we say if you have some function and it simplifies to some other function, and you're trying to find the limit of f, but you can't find the function value of f, instead, look at the limit of g. And hopefully your simplified g has a function value at c, and the limit of f will equal that g's function value. Okay? We essentially remove the location of the hole. We remove the hole with this new function and replace it with just a point. And then we can use that point and we find the location of our limit. All right? Now, what if a function can't be simplified? Let's take an example like this. Limit as x approaches 3 of 5 over x minus 3. Well, again, my first attack to find this limit is to find the function value. Okay, because if the function value exists, typically the limit will equal that. But I get 5 over 0. Again, you cannot divide by 0. We are undefined. But I look at this and I can't factor anything, and I can try to manipulate stuff, but it's not going to change anything. Okay? Instead, we're going to say that this limit actually does not exist. And why doesn't it exist? Because this location, x equals 3, is a location of a vertical asymptote. Our function will approach the line x equals 3, but we'll never get to it. And we are definitely not approaching the same value from the left and from the right of 3. We're approaching one of the infinities, positive infinity or negative infinity. But then you're probably saying, well, how am I going to know if I have a limit and I can find it and I can simplify, or I can't? Well, the shortcut, the key trick is if you get 0 over 0 when you try to find the function value, that is your indication that you have a hole. And when we have a hole in our function, it's typically in a situation like this, where we are approaching the location of our hole from both sides, so the limit exists. So when we see 0 over 0, assume the limit exists. And you need to simplify your function to find that limit. If you get a number over 0, that's the indication that you have a vertical asymptote. And that the limit does not exist. All right, so to kind of flow chart things out, if you want to find a limit analytically, step 1, you should try to find the function value. If you get a number over 0, your answer does not exist. If you get 0 over 0, your limit exists, you need to simplify. And you're going to continue to simplify until you can plug in the value and you find g of c, which equals a number, not 0 over 0. Now I'll tell you, for all of the rest of the examples that we do in class, we're going to get 0 over 0, okay? However, when you're practicing and when we move forward, it's always beneficial to check, because you might just assume that you're going to just start simplifying, start factoring, start doing some algebraic techniques, and you might do some stuff and it works out, but if you go back to the original function, turns out you could actually plug in the value and you get an answer. So doing all the simplification was unnecessary. All right, but for these examples, the rest of our examples we're going to do, we are going to have situations where f of c, in this case f of negative 3, is 0 over 0, which means we have a hole on our function at this x location. Let's look to algebraically simplify, remove the hole, find the location of our hole with our new function. All right, and this is where it turns into a review of algebra. Okay, we need to be able to factor a quadratic. Know that we need two numbers that add to get to our middle coefficient and multiply to get our third term, positive 3 and negative 2. We can then remove the x plus 3's. We have multiplication. When we have multiplication, simplification is easy to do. Creating this new function x minus 2. And to find the limit of this function, it's the same as finding the limit of this function. It's simplified form, where we would just find its function value, which tells us the location of the hole. In this case, it's negative 5. So this original limit is negative 5. We found the location of the hole we know that if we plugged in negative 2.99999 into this, we'd get a value that's very, very close to negative 5. All right, you guys try the second one. Check the answers with a neighbor. I'm going to tell you right now that if you plugged in negative 4, you would get 0 over 0. You have a whole, simplify. All right, go ahead and check with a neighbor. Let's make sure we're getting the same answers. I got 4 as well. Fantastic. Let's move on to the next one. Anybody have any questions about this? Remember, the final step is to plug in our value for x. Okay, we want to make sure we don't forget that step. This guy. So this has there's 2 quadratics with leading coefficients that are different than 6. There are many different ways to factor these. I'm sure you have learned your own ways in the past. I have my trick way that I do, and then I also have a way where it's just I figure it out. I'm going to show you my trick way. Maybe you'll learn something. Because most teachers don't teach this because they think it's like not mathematical enough. But if you look at the proof of why this works, you realize that like, whoa, this is crazy. And this proof is very complex. But let's take 6x squared plus 7x plus 2. Now, a lot of teachers teach you to multiply that a by c. They don't tell you why, they just say do it. Okay, well, I'll say do it too. And then they say factor normally, but then write out the middle term as your correct factor. So it's like x squared plus 4x plus 3x plus 12. I'm just going to write it as x plus 4x plus 3. Okay, then I will take my a value and I will divide both of these by that a value. Now watch what happens after you simplify, and you want to simplify completely. You end up getting the roots of the equation. It doesn't give you the factored form, but it gives you the roots, negative 1/2 and 2/3. And then to get the correct factored form, whatever's left in your denominator, throw that in front of the x. And we get the correct factored form, 3x plus 2 and 2x plus 1. Isn't that neat? Did anybody learn that method? Yeah, one person, 2, 3. It used to be taught like all the time because it was like quick, boom, easy. And then they moved into change this into x squared plus 3x plus 4x plus 12, but keep the 6, and then factor by grouping. The problem with factor by grouping is like rarely are things factored by grouping, and it works out so nicely. It works out in this situation nicely, but I don't know if it helps out students so much. 4x plus 3. What? Is it, what did I, oh, it's a 2. Sorry. So this technique also works. And you have 3x plus 2, 2x plus 1. And then the last technique, which I'll show you for the bottom one, is just by figuring it out. Okay? And that's what teachers only taught back in the day, because the other ones are like a little bit mysterious why they work. So it used to be, okay, you have your first term, 2x squared. You know the only two numbers that multiply to get 2x squared are 2x and x. So you go ahead and place your 2x and x down. Then you kind of know that you either have 2 and 2 or you have 4 and 1, and one of them has to be negative here. And then you kind of just do the math in your head, and you think, okay, I need my middle terms to add up to be negative 7x, and I need my back terms to be negative 4. So I'm thinking maybe if I have a negative 8 and a 1, so maybe 2 times a 4, and then a 1 times an x. Well, if this is a negative 4, and this is a positive 1, 2x times negative 4, negative 8x. 1 times x is 1x. Added together, you get negative 7x. Maybe you do it that way. Okay? But that's all a review of factoring. Whatever way works for you, great. You will find you will not have to factor many things with a different than 1. And if you do, they're usually very simple with like a 2 instead of like a 6 or something. All right, so let's finish it off. We do have to work with fractions often in this class, so make sure you are comfortable adding and subtracting fractions and whole numbers and stuff together. Negative 1/9. Anybody else get that? That looks right. Okay. Sometimes we're not going to be factoring trinomials, quadratics. Sometimes we will just factor a greatest common factor, or we'll try to simplify things. Now, I want us to be careful with something like this. Okay, we take a look at this, and some students want to do this. Okay, don't do that. It's illegal. Okay, this is why addition is not my friend sometimes. When it comes to simplification, this doesn't work, okay, because of the addition in between them. Some ways, maybe your algebra is rusty. Maybe you're not sure if you can do certain things. Ways to check to see if you can do it or not is use numbers. Let's say you have 2 plus 3, and then you have 1 plus 2. Well, if I evaluated this, this is 5/3. But if I crossed off the 2's and they just went away or they became 1's, you'd end up with 3/1. Not the same, okay? So if you're ever confused or not sure, use some numbers and see if it works. That doesn't work, so get that out of here. and get that out of here. Instead, what we want to do when we see addition is to create multiplication by factoring. What do 8x cubed and negative 9x to the fifth share? An x cubed. You can divide it out of both of those terms. Same for the denominator. X cubed. It's gone. Now that we have multiplication, multiplication is simplification's friend. You may now cancel these x cubes. Try something like, 2 times 1 plus 3 and over 2 times 4 plus 5. Having the 2 here or not having the 2 here is not going to make a difference. So we need to find the limit as x approaches 0 of this new guy. We are able to plug in 0. Okay, cool. Next type. Different looking. Can't really factor this, but I see I have a 4 plus h squared. Notice I have an h now, so I'm going to be plugging in 0 for h every time. Okay, and just to confirm things, if I plugged in 0, I would get 16 minus 16 over 0, 0 over 0. We have a hole, we have a limit. Let's find the location of that. Just make sure you do not tell me that 4 plus h is 16 plus h squared. Instead, we know we have to distribute everything to get 16 plus 4h plus 4h plus h squared, which is 16 plus 8h plus h squared. Okay, fantastic. We distributed it. Can I plug in 0 for h? No, I still get 0 over 0. But I see I have a 16 minus a 16. So let's take care of this 16. It's gone. Now I have 8h plus h squared over h. I try to plug in 0 for h. I still get 0 over 0. Continue to simplify. Well, I can factor out an h. H times 8 plus h. I can then cancel these h's. And now I have 8 plus h. You're not done. That's not your answer. Remember, you're trying to find the limit as h approaches 0. Make sure you plug in 0 for h to get your answer 8. All right, do the next one. It's very similar to this one. It has 2 variables. Yes, Mr. Siddiqui?
Is it okay to look at it like the difference 2 squares?
So factoring it as 4 plus h minus 4 and 4 plus h plus 4, that works out. Yeah, cool. Yeah, you can do it that way. I never thought about it that way. Try this one, either way. You will get an answer that involves x's. Okay, you have 2 variables, but the limit is h approaching 0. So you'll eventually plug in 0 for h. Go ahead and give it a shot. Check your answers with a neighbor. Good. I did not hear many people include H in their solutions. They went straight to the correct answer, 2x. After we simplify everything, we end up with 2x plus h, but we did not forget to plug in 0 for h to get our final answer, okay? We should always be thinking about plugging in 0 every step along the way, and we stop when we get something other than 0 over 0. All right, so there are more complicated distribution problems if you want to try them in the homework as well as in the review. Next technique, this type of function. It's got a square root in it. I can't plug in 0, I'd get 0 over 0. What am I to do? Well, we will use the technique of multiplying by a conjugate. We're going to use this whenever we see square roots. Now, how does this help us? Because when we multiply something by the conjugate is just the same thing with a different symbol in between. So if it's a minus, you put a plus. If it's a plus, you put a minus. The reason why we do this is because it ends up being a difference of squares, where we have a squared plus ab minus ab minus b squared. And the ab's will cancel, giving you just a squared minus b squared. Which is helpful if squaring something simplifies it. And when I square a square root, the square root goes away. So I'm going to multiply the top and the bottom, because it's a version of 1, by the conjugate. Now, where people make mistakes here is they think the conjugate is whatever's inside the square root, and they multiply by x minus 1. Root x minus 1. But that's not the conjugate we are looking for. We actually want to square all of this term, which is why we consider that entire square root a. And 1 is b. So I'm going to multiply this by a plus b, or multiply the top and bottom by root x plus 1 plus 1. Make sure you multiply the top and the bottom, or else you'd be changing what you have. We can multiply things by a version of 1. Anything times 1 is itself. All we're going to do is make it look different. Okay, after we multiply, we get a squared minus b squared. Well, root x plus 1 squared is just going to be x plus 1. 1 squared is 1. Please be careful, though. We are squaring 1. In the future, if you have something other than 1, make sure you square it. Now, in the denominator, usually our algebraic instincts is to distribute and to take this x and to move it into those. Don't do that. That complicates things. We want to keep multiplication. Multiplication is simplification's friend. So keep this as x times root x plus 1 plus 1. All right. Let's go from there. The ones, they're gone. We have x over x times root x plus 1 plus 1. We can cancel these x's. And now that this x is canceled, I can plug in 0 and get something other than 0 over 0. So I will finish off by finding the limit as x approaches 0 of this. All right, do the next one. Remember, conjugate so that you get a squared minus b squared. Make sure you're squaring the b. Squaring both of the terms. All right, I got an answer. Who else get an answer? Very nice. We're off a little bit. There we go. There we go. If we got the answer and our neighbors have not, excellent. Let's go ahead and help our neighbor out. Very good. Excellent. I don't see anybody making the mistake that I've seen. We'll talk after class. Cool? You're all set? All right.
Still working on it.
That's fine. Do that 5 minus that 9. So what I didn't see, which I was surprised to see, is somebody tell me that the square root of 9 is plus or minus 3. So we did that. Thank you for not doing that. It means your pre-calculus teachers did not lead you astray, or one of your teachers didn't lead you astray. That's not correct. The square root of a positive number is a positive number. You guys know that, okay? It is when you are solving an equation like this that the plus or minus pops up. But when does it pop up? It's not in the first step after you square root. The square root of 9 is not plus or minus 3. The square root of 9 is 3. It is the fact that the original value x could have been a positive or a negative number. But when you square it, it's automatically a positive. But when you go back to its original form, it's important to know that the original value could have been positive or negative. Okay? And then that plus or minus moves over to the 3. A good job for not doing that. Might as well try the next one as well. It's A plus B, or A minus B. So you don't change the A, you don't change the B, you just change the symbol in the middle. Nope. Nope. Because you'll still get A squared minus B squared. Can I cancel 16 minus x with x minus 16? No, not as it stands. But if I factor out a negative 1, then all of a sudden we'll have negative 16 plus x, which is the same as x minus 16. All right, we should be experts on this conjugate process by now. Anybody, we should get negative 1/8 for all of our answers. Move on to the next type of algebraic manipulation. Does anybody need the previous one up a little bit? Oh, you were good. So we have fractions inside of fractions. This is ugly. If I plugged in the value -4, I'd get 0 over 0. Okay? So we have a hole. We need to algebraically simplify to find the location of the hole. Again, this is more algebra review than calculus. The calculus was from last lesson, but it's okay. What we're going to do is eliminate this fraction inside of a fraction. Let's combine these two fractions up here. How do I do it? I'm going to have to give them a common denominator by multiplying the top and bottom of each other by the other's denominator. By doing this, I get x over 4x plus 4 over 4x all over x plus 4. Now, just like fractions with common denominators, if I have the same denominator and I add the two fractions together, the denominator doesn't change, it's just the numerators. So make sure you do not add 4x and 4x. Instead, you just have x plus 4 over 4x. Now, this is still kind of ugly. I have a fraction inside of a fraction. But what I like to do here is, instead of dividing a fraction by something, instead multiply by the reciprocal. Change this into 3/4 times 1/2. Right? We know we can do that. That becomes 3/8. I'm going to change this into x plus 4 over 4x times 1 over x plus 4. We could cancel now, or we could cancel later if we're not comfortable with canceling now. I mean, you could literally flip-flop the 1 and the x plus 4. We're talking about multiplication here. We can move everything into one fraction if we wanted to, and just have these separated by some parentheses, however you want to know that you're allowed to do that. Finishing off with this, getting our answer, negative 1/16. Okay, let's try the next one. Let's see if we can tackle one of these common denominator ones. Two more. I got negative 1/9. Negative 1/9. Classic algebra error of not distributing the negative to both the x and the 3. So it should be 3 minus x minus 3. Yep. Now you combine these, the denominators stay the same, 3 minus this entire thing in the numerator. Yep. Now, if you had that here, this can't cancel. Okay? This is like that mistake I showed you. We don't have multiplication up here. But I have a 3 minus a 3 up there. That's what's going to go away. So this 3 is going to stay down there. These 3's do cancel, which you're good at, okay? Now I would move that divided by x to be times 1 over x. That way you know that x and that x can cancel. Now you plug in 0, you're going to get your answer. Work is up here. I kind of tried to show step by step, leaving no doubt what things should look like. Okay? The 3 minus the x plus 3, we must distribute this minus sign to both the x and the 3. So it's 3 minus x minus 3. We cannot cancel a 3 here with this 3 down in the denominator because we do not have multiplication in the numerator. But after we get rid of these 3's, we essentially have multiplication, -1 times x. So I can cancel these x's, giving me -1 over 3 times x plus 3. Some of you distributed the 3 into the x plus 3 and got 3x plus 9. In this case, distribution didn't hurt you. So you end up with -1/9. Let's make sure everybody has that work down. Some of you did great at it. Some of you was a little bit of a struggle. If you are one of those that are struggling, guess what? You will need to practice. For all of you, the Band-Aid gets ripped off next class. We will not have time to do lots of practice problems because it takes a while for students to finish the quiz. So we'll do maybe 1, maybe 2 practice problems and then quiz, okay? Rather than like 5 problems that are like very, very similar to the problems you're going to see on the quiz, okay? So this will be the first quiz where people are like, ugh, that was rough. Well, most people will be like that. I know some of us have struggled so far, and that's okay. If you're struggling, guess what? You just have to work harder than everybody else. That's life. Okay, going to the challenge 1. Now, here's what we got to think about. Okay? I like to think about math as being like a game. Okay, they're like puzzles. You just got to figure out how to move the pieces around to solve the puzzle. Okay? I think about this as a puzzle. Okay? And I also think of it like a game. And when I go to this problem, I like to think about chess. Does anybody play chess? Okay. So when you play chess, or really any game where you're competing against somebody else, it's important to think ahead. It's important to not just move. Okay? You want to try to think a couple moves ahead. Because if you make a move and it's a mistake, it's going to cost you later. Okay? Well, before you start doing stuff, think about it. Okay? It looks like we have like 2 moves to make. We could either combine these 2 fractions using a common denominator. Okay? Or we could get rid of that square root by multiplying by the conjugate. I'd like you guys to think of those 2 moves, those first 2 moves. You don't have to know what the second or the third or the fourth move is going to be, but at least think about the comparison of those first 2 moves and make the correct move. Okay? Go. Wait, before you go, discuss with your neighbor, what's the correct move here? Yes. What did you do? And you've already started this? You tried to go common denominator, right? Right, now it's best to start over again. Start over. You can. you're gonna have to just do things like multiple times. It's gonna be a mess if you do it the other way. Yes. I forgot what the answer was.
So I just multiplied by this conjugate, and
Yep.
I got that on top.
Yep.
Of like,
You got it.
multiplied by 2x plus.
All right. After thinking about the first move, I realized that if I multiply the top and the bottom of root x plus 2 of the left guy, this denominator turns into x minus 4, which is the same as this denominator. So we combine those two fractions just by doing that. So now we have root x plus 2 over, this ends up being x minus 4, and then I still have this as 4 over x minus 4. Well, man, that made things easy for me. I can just combine this to be root x plus 2 minus 4, or root x minus 2, over x minus 4. If I plug in 4 into this, I get 0 over 0. All right, I give up. Already multiplied by the conjugate, Mr. Messner. This must not work. Don't write that down. When you get 0 over 0, what are you supposed to do? You keep going. I get 0 over 0. You got to keep going. Guess what? Multiply by the conjugate again. Oops. Okay, so think chess, think ahead. Don't just act without kind of analyzing, seeing what the right move to make is. You will find when you practice, and you should practice, that certain problems will look similar to other ones, and the algebraic technique that you should use should kind of reveal itself just by looking at it. Oh, I need to multiply by the conjugate. Oh, I need to find the common denominator. Oh, I need to distribute and simplify. Okay? Oh, I need to factor. You'll just be able to see it. But if you don't practice, you're not going to see it. And